So yeah, in the first half of the talk, I will introduce the background of the problem and why this result matters. And in the second half of the problem, the talk, I will try to convey the idea of our algorithm. There are some parts which I didn't even dare to describe here, but so that I can convey so I try to like choose some contents of our paper so that it can be somehow contained to non-TCS audience. So the message of the day are twofold. So one is like we obtained one technique which is able to handle computationally hard cut problems. I will like in a minute explain what we mean by cut problems, which is weight friendly and also able to reveal non-extremal cuts. So especially our technique enables us to obtain an algorithm for which the existing techniques couldn't handle. So most notably, we obtained an algorithm as a major application of the technique for coupled mean cut and its generalization. And with this, we could settle a trichotomy of parameterized complexity for mean set gamma. So even if you don't understand some notation here, don't worry, it will appear like at some point during the talk. So what do we mean by cut problems? So by cut problems, we mean problems whose solution is a union of cuts or a cut, or for which handling cuts is an important subroutine for designing algorithms. So so probably the most well-known cut problem is a minimum ST cut problems. You are given two source and sink, and you want to find the minimum cut. It can be weighted or cardinality, and for both versions, we know that this problem can be solved efficiently. Maybe some of you might have heard of multi-way cuts. So here you are given a graph and a subset of vertices which you declare as terminals, and you want to find minimum number of edges so that when you delete these edges, all the terminals are in distinct connected components. So you want to pairwise disconnect the terminals. So a more like refined version of multi-way cut is multi-cut. So here you have cut requests which come as pairs of vertices, S1, T1, S2, T2, so on and so forth. And you are really targeting to disconnect these paired, the paired vertices. And there are many other problems which we can call cut problems. And these types of problems have been extensively studied both for approximation algorithm and parameterized algorithms, and led to many generic techniques for designing algorithms. So here, in this paper, we care about parameterized complexity. So I will focus on algorithm design technique for FPT algorithms. But maybe I can remark here that some of the techniques that I briefly present in this slide, they are also like all well employed to design approximation algorithm for similar types of problems. So probably the standard and like most like prominent technique for handling cut problems is greedy method. So by greedy method, we mean that we want to enumerate extremal cuts. So if we only care about cuts of size m most k and minimal cuts, then extremal cuts can be efficiently enumerated. By efficient, I mean in FPT time, because such extremal cuts are known to be m most 4 to the k if we care about the size of the cut m most k. And this is also both for edge and vertex version. And so this method was introduced earlier by Max 2016, and like later Max and Rascon, they solved multi-cut problems. So using one more technique, which is built on top of this greedy method. It's called shadow removal. Multi-cut problem. So I want to mention that multi-cut problem was, by that time, that when they solved it, it was like arguably the most important open problem in computational complexity, and it was open for a long time. And like at that year, Max and Rascon, and there was another team who simultaneously and independently solved the problem. Another method is called tree width reduction. So basically here they reduce the tree width of the input graph into bounded tree width, while preserving the number of cuts projected on the tree width. So yeah. So recursive understanding via randomized contraction. So it's like we find sparse cuts and then like divide the instance into smaller instances and recursively find the sparse cuts until you end up with an instance where you cannot find a sparse cut anymore. And for problems for which are tractable on highly connected graph, they tend to be efficient. They tend to have FPT algorithm via this method. So many results were obtained using this technique. The last one I want to mention is a relaxation-based method. So maybe some of you already know the vertex cover. So when you formulate it as an LP, then it has half-integral property, meaning that there is a fractional optimal solution where all the values are 0, 1/2, and 1. And also this property is known for multi-way cut as well. And using this half-integral property, they do some like very fast branching algorithm, which led to like a breakthrough running time by Saigon and some others in 2013, and later this was developed in many ways. So now there are several ways of obtaining relaxation of these cut type problems other than this half integrality. And like often the algorithms based on these methods, they are linear time algorithm, and the exponential dependency is the best they could obtain. So there are these beautiful techniques for handling cut problems, but there is some really basic cut problem which seems to be out of reach using these existing techniques. So one is bi-objective ST cut. So basically it's weighted min cut. So I want the size cardinality of the cut to be n most k, while we put also weights on the edges. So I want both the cardinality n most k and the weight sum of the cut to be n most w. So it is known that it's FPT when you consider both k plus w. So it's like f of k plus w times n to the c algorithm exists. But can we obtain FPT algorithm in terms of k only? So this was not known until our work. But it can be easily seen that there is an efficient algorithm if k equals the max flow value, like value in terms of cardinality between S and T. So here in this talk, lambda always represent the min cut size or max flow size, which are the same. So in this particular case, you can solve the problem efficiently. So how? So you just update the weight by adding this big constant W, which is the upper bound, like the budget for the weight sum. And now you ask run the minimum weighted min cut algorithm to answer whether there is an ST cut of weight at most k plus 1 times W. So like any cut which uses more than k cuts will never qualify as such a cut. So only cuts of using exactly at most k will qualify for it. But there is nothing which uses less than k. So if there is such an weighted cut, then we know that it uses exactly k edges, and the weight sum will be at most W. So then you might ask, why can't we use the same reduction even when you don't have this guarantee? So even when k is larger than lambda. Even when k is larger than lambda. So in this case, like, okay, maybe you could find k plus 1 times W weighted cut, but maybe it uses like way smaller than k edges, and the weight sum is way larger than W. But it could somehow fool, but still, like, because it saves a lot of factor here, so although it exceeds the weight bound, it still qualifies as a min weighted cut. So this can happen. So only with this guarantee that k is exactly the min cardinality cut, you can use this reduction. So this problem is known to be NP-complete. So it will be fantastic. So using this argument, so one might wonder, what if we can like add some edges so that the min weighted min size cut z is still a cut, and somehow this z happens to be the min size cut. Like, so if you can lift up the size of the min cut so that this condition is somehow satisfied, then now you can apply this efficient algorithm and solve the problem. So that's the idea. But of course, the cut z, the min weighted cut as z is hidden, so you cannot just blindly add edges to lift the size of the min cut. This is not possible. But so this is our first contribution in this direction. In polynomial time algorithm, with a pretty good probability, so it's 2 to the minus k log k, roughly, with that probability, if you have the guarantee that the cut z you are looking for is minimal and is of size k, or at most k is the same, so size k, then you can actually add edges so that z becomes the minimum ST cut, cardinality minimum ST cut. So okay, so let's see. So there is a randomized algorithm such that so the input is given graph and 2 terminals S and T, and you're given an integer k. So this k is supposed to be the bound of the cut that you are looking for. Then in this time, and it runs in linear time, then you can find an edge multiset. Like, okay, so it's an edge multiset, not in the original graph, but something that you can add, so that now after adding this edge set A to G, the ST min cut size goes above K. And so this is the output. So you always output such edge set A, and for any minimal ST cut, so this Z might satisfy some additional constraints, maybe might have minimum weight and so on, but for any minimal ST cut of size K, then with a very good probability, Z is actually still remains an ST cut. So you can avoid destroying Z being ST cut when we add edges A with a good probability. So that's the point. So this is very nice because, like, here we don't make any other assumption about this ST cut Z except that it's minimal. So you can attempt to consider some cut problem where Z satisfies some weird conditions, and then still with a good probability, you can make it a tight ST cut, like a minimum cardinality cut. Does it
say a minimal ST cut of size K? Do you mean that it's a minimal ST cut that happens to have a size K, or do you mean that it's a ST cut of size K but that is minimal? Or I was a bit confused.
So minimum, yeah, it's a minimum. So if you delete one edge, then it's not an ST cut anymore, and it has size exactly K.
So graph might have a minimal cut of size less than K, right?
Yeah.
So you don't care about those.
Yeah, we don't care about those. So like usually that issue is very easy to resolve. So you just increase from very low value for K and then apply the algorithm like repeatedly for each increased number K.
I see.
So if you know that you care about minimal ST cut of size at most K, then you do this for K for 1.
So this, what you care is a minimal cut that happens to have size K.
Yeah.
Right. So minimality doesn't apply to size.
Yeah. Okay, so any question to this point? So I hope
that this part is clear. So, okay, now we can apply this algorithm for, so for the previous problem, this bi-objective ST cut problem, we can apply this flow augmentation algorithm and make this minimum weighted mean cardinality cut Z as a mean cardinal, So we can make Z of size n most K to be the mean cardinality cut of the entire graph by applying the flow augmentation algorithm. But you need to consume like FPT time because you have the probability is 2 to the minus K log K, so you want to repeat it that many times. But then after that, you will succeed. And okay, one more thing. So it means that with this technique, we immediately prove that bi-objective ST cut is FPT. So one thing to remark is that during the talk there is a lot of time I say that we guess with probability something or we obtain something with certain probability, but everything can be easily made deterministic. But then I need to say instead of probability, talk about branching, which is more complicated. So I'll just say that we can guess something with certain probability, but everything can be made de-randomized. Right. So there is another problem, which is a little more exotic than this bi-objective ST cut. That the existing nice techniques doesn't seem to cope with. So this problem is called the coupled mean cut. Here the input is graph G with 2 vertices S and T, and you have budget K. And on top of that, the edge sets are, let's say they are partitioned into pairs. So maybe subset of them are partitioned, but that's for simplicity, the edge sets are partitioned into pairs. And then the question is, we want to find an ST cut. So here I didn't say minimality. So we want to find an ST cut which consists of at most K pairs and K pairs. And furthermore, for every H pair E, F, which is where Z doesn't contain, where none of which is contained in Z, then at most one of these two edges are fully reachable from from the source in G minus C. So what do I mean by this? So let's say the edge set Z can look like this, and some of the edges might be like here. So it means that if E, F is a pair, then you cannot have E and F fully reachable from S. So by this blob, I mean the set of vertices reachable from the source after deleting G minus C. Does it make sense? Yeah.
So every pair not G, but in I
Yeah,
see.
so
Every edge is
if
pair.
yeah,
Okay.
so if this pair is already violated by C,
Then like they cannot be fully not both of them can be fully reachable from S. So like, okay, maybe this is a little more complicated. It's simply saying that for every edge, not all the four vertices cannot be reachable from S in G minus C. That's another way of saying it. Yes.
F is already designated in the input.
yes,
Oh,
yeah. So they are partitioned into pairs. So the pairs is part of the input. Right. So is this problem FPT? So that's the first question. And why do we care about this problem? So yeah, let me spend
some time to convince you that it's worth caring about this problem. So like for this we need to introduce what is called mean set gamma. So it's a constraint satisfaction problems, if you heard of it. But you can think of it as an alternative way of expressing some combinatorial problems. So okay, let's express min cut in a different way. So you are given this min cut instance G and the source and sink S and T. Then from this input, we take the variable as the same as a copy of the vertex set. And for every edge of the graph, I introduce the constraint that U should be the same as V. So I introduce the equality constraint. And then I introduce two constraints which designate the source as 1 and the sink as 0. And I declare that, okay, I never want to violate these constraints. So you can, yeah. And then you ask, okay, is there Boolean assignment on the variables, like Boolean, like 0 and 1, so that at most k constraints are satisfied? No. Yeah, everything except for k, at most k constraints are satisfied. So you can quickly check that these two problems are given. So if you make this formula in this way, in this particular way, then min cut is yes instance if and only if this problem is yes instance. So because we make S equal 1 and T equal 0 as crisp constraints. Crisp constraints means that we never want to violate it, and we can enforce this condition by making like more than the budget number of copies of each constraint. So it will never be violated. Okay, so suppose that you have, suppose that the min cut is size most k, then like all vertices reachable. After removing the min cut, okay, let's assign it 1, and all vertices not reachable, so which means reachable from T, they get value 0. Okay, then all edges which are where both of them are reachable from S, their corresponding constraints will be satisfied. So anything which is violated will be of this form, which are crossing this reachable and non-reachable sets. So that exactly counts the number of cuts. And the opposite way is easy to see. So because these are crisp constraints, you have to assign S equal 1, T equal 0, which means that if you walk along the path from S to T, there should be at least one edge where this value changes. Right? So the violated edges will exactly correspond to the constraints where this change occurs, and then you can create the corresponding reachability set, unreachability set, and the cut, which has size most k. Yeah.
So in the flow augmentation theorem, when you say ST cut, is that an edge cut? Is it?
Yeah, everything is edge cut. We don't have a vortex version.
Because I was confused with the bi-objective STK problem where the
yeah.
weights are on the vertices.
Alright, so the weights are on the edges, and we want to find edge cut.
Okay, so even on that problem.
Yeah.
Okay.
So because our tool is for edge cut, so all the problems that I mentioned here will be about edge cut.
Okay.
What do you mean about copies?
Copies, so you have the same constraints multiple times. This is allowed.
So you're adding same t equals 0, k plus 1 times, so that if this one is satisfied, no matter how you delete k constraint, you still cannot satisfy unless you satisfy this.
Okay, so here
We use two types of constraints. One is equality constraint. Three types of constraint. One is equality constraints. The other is like setting a variable into 1. The other setting is a variable into 0. So we have three types of relations. So this collection of relations is called language. Like a set of relations is called language. And if the arity of each one is finite and the number of relations is finite, then like gamma is finite. So in that case, we say it's finite. And if we care about the Boolean assignment, then it's called finite Boolean constraint language gamma. And so just like in this example, you can make constraint by applying some relation to a tuple of variables of the same arity as the relation. So here, equality has arity 2, so I can apply it to tuple, a pair of vertices. 0 and 1, they have arity 1, so I have to apply it to a single variable. So if you are given a set of variable v and specific language gamma, then you can make a formula as a conjunction of constraints. Your constraints are obtained by applying the relation on the tuple of variables. Right? Then you can now talk about maximum satisfiability of formula. So if a constraint is violated, I pay 1. If it's satisfied, I pay 0. Then you want to have a Boolean assignment such that the costs of the assignment is at most k. So that's exactly, so we have just expressed mean cut exactly as such a problem where the relation is equality 0 and 1. Okay. Yeah, I guess I will probably won't be able to cover much of this algorithm part, but let me try to at least convey the flavor of the result. Yeah. So another problem that you can express as means at gamma is a k-clique. So consider k-clique as a parameterized algorithm. And it is known that k-clique problem is FPT equivalent to k multicolored clique. So FPT equivalent meaning that one problem can be solved in FPT time if and only if the other problem is solved. So what is k multicolored clique? So you're given a graph, but now with a partition of the vertex set into k sets. And each vertex set is an independent set. And there can be edges between different parts. And now the task is to find the k-clique, or decide that there is no k-clique. So if you have a k-clique, of course you have to choose exactly one vertex from each part.
Oh, so each is stable.
Yeah, each VI is stable.
Is it complete multipartite?
Not complete multipartite. Then this problem is easy. There is always k-clique. So the edges between different parts can be arbitrary.
And yeah, this problem is FPT equivalent. And also furthermore, you can assume that each independent set has size exactly n. So now, you can formulate this k multicolored clique as a mean set where gamma uses these three relations that we saw before. And on top of it, we use double equality. So for this double equality, So the error t is 4. So when it's applied on these 4 variables, these 4 variables, the assignment satisfies this constraint if A equals B and C equals D. So that right. So okay, so I will first show a reduction from multicolored k-clique to some graph cut problem. And this cut problem is very easy to see that it can be expressed as mean set gamma with this double equality in addition. So how do we build it? So I built like so I add this source and sink, and I make the copy of V1 up to Vk. So I named it as V1 and this is V1, but they are different vertices because it belongs to this capital 1 and this belongs to capital Vi. Right, and between any I and j which are distinct, I add vertices which like Vij and Vji, where these vertices represent the edges between the vertex at Vi and Vj. Right, and also so I fix an ordering between on the edge set between Vi and Vj, so and they follow the same ordering. Okay. Right. And we make also k choose two edge disjoint cut in the following way. So from S to V1 you add some edge. So the first vertex in each part I add an edge, but I add multiple copy of it so they will never be chosen for meaningful cut. And between V1 and V2, I add a path from V2 using the vertices using the vertices of Vij, where all the vertices in between, they represent the edges incident with V1. So for example here, E1, E3, E4, these are incident with V1. And these are edges between Vi and Vj. Okay. Also between V2 and V3 we do the same. So this path like from S to Vn will go through all the vertices in Vi, and also it will go through Vij. And there will be like Vij for different j. So there will be multiple edge disjoints that go through this Vi simultaneously. So they are all edge disjoint, but they share the vertices on V1, V2 up to Vk. Right. So now suppose that there is k multi-way cut. So I choose k multicolored clique. So these correspond to k multicolored clique, and there is an edge between every pair of vertices. So then I choose the cut. So also I need to designate the pairing. So for every vertex which corresponds to some specific edge in the original graph, I pair it with the so if I look at this edge E4, then I pair this edge, the edge that leaves this vertex, to the edge that leaves the corresponding vertex. So this gives you the pairing of edge sets. So some edges will not be paired, but like many of them will be paired. So doesn't make sense.
I'm trying to understand. So if, let's say V1
Yeah.
in the group VI
Yes.
are adjacent to 3 vertices in Vj, you're
Yeah.
saying V1 will be adjacent to E1, E3, E4,
Yeah, exactly.
right? And how do you make the pair of E1 and E3, or E3 and E4? How do you make
Oh,
that?
so we make a pairing between edges, not vertices. So,
Right.
so edges in this graph. So how do we make the pairing? So this E1 and this E1, they actually correspond to the same edges in the original graph. Then for edge, there is a single edge leaving E1.
And there is a single edge leaving E1, and I pair these two edges.
What is the single edge coming out of E1?
So when I add,
When I add a path between V1 and V2 via Vij, the subpath from V1 to V2 visits all the vertices, like E1, E3, E4, that correspond to edges that are incident with V1, following this fixed order. Yeah. So between V1 and V2, there is this path, but for different, there will be like a different Vij, where j is anything from 1 to k except for I. And also there is a similar copy of it, and V1 and V2 will have a path going through that part. So between any two vertices, there will be k minus 1 vertex decision path.
So that's a way of describing all the edges incident with the V1 in that sense, right?
yeah,
Uh,
yeah, exactly.
And you're fixing the order of
Yeah.
this.
Okay, but what I didn't understand now is why is B2 here now adjacent to E4 in that?
Oh, so for the last vertex, I just connected
okay.
to V2.
That's just an
Yeah.
arbitrary choice.
Yeah,
okay.
yeah, that's
okay.
arbitrary.
I see.
So
But that would be the last edge. So
Last edge in the
yeah,
order,
yeah,
which
yeah,
was
exactly.
incident to
Yeah.
V1. Okay, I understand.
so it's always like a long path.
Yeah.
Okay, can you also now repeat how you pair the edges?
So
Yeah.
like for every edge in the original graph, there are two corresponding vertices. So if the edge is from Vij and between Vi and Vj,
Yes.
then the corresponding vertex will appear in Vij and Vji.
Yes.
So and this vertex is degree exactly 2.
Yes.
Right, because it's a part of
So
path.
I just consistently choose the leading edge. I can maybe consistently choose the incoming edge, but okay, let's say I will choose the leading edge.
How are the edges directed?
Like from S to T, so like
Ah.
yeah. So I choose the leading edge and the leading edge from here, and these two are paired. And because I chose the leading edges consistently, they do not overlap.
Are you reducing to the coupled mean cut or
No. I'm reducing to mean set gamma.
with the double
Yeah,
equality?
with double equality on top of it. Yeah. So okay, maybe I will. Okay. So then the instances are like equivalent. So I'll maybe skip this part.
So why this problem? So now I'm looking for mean ST cut of cost k choose 2. Okay, so this is the problem that I want to solve. Mean set gamma with cost this. Then you can imagine that if you have a k multicolored k-clique, then I look at all the edges between the clique and then I choose the corresponding edges which form pairs, and that will be the correct SD cut of cost k choose 2. So the cardinality of the cut will be k times k minus 1, but the costs will be k choose 2 because we will choose the paired edges. Right? And actually the opposite way also holds. Right. So when you allow like a one additional relation, this means that gamma could emulate some hard problem, W1 hard problem. So W1 hard means that it's unlikely to have FPT algorithm. Okay, so I remarked that coupled min cut can be also emulated as a mean set gamma where you have some special relations, some relation. And so I mentioned that this edge multi-way cut was like one of the major open problems in like 10 years ago. And actually the multi-cut, this edge multi-way cut can be reduced to some other problem with a standard technique. And this other problem was the hard nut of this multi-cut. So the core of the paper of Max and Rascal was to resolve this bipedal multi-cut compression problem. And you can actually reduce this bipedal multi-cut compression problem into coupled min cut. So this means that if you can have FPT algorithm for coupled min cut, then you can solve the really hard part of multi-cut problem. So that's exactly what we do. So we resolve that coupled min cut is FPT, and actually some generalization of it. I will not describe what this generalization means. And also for Boolean finite constraint language gamma, we established trichotomy of this problem. So for any such gamma, one of the following, we could prove that one of the following holds. So either the language can implement some directed cut. So U implies V. And this we interpret as directed cut. And what we mean by implement is a bit technical to define. But basically, the idea is that even if gamma doesn't have this relation like immediately, maybe you can combine some other relations and add some dummy variables to mimic and enforce such a constraint. So, and this can be formally defined. So either gamma implements some directed cut, which is out of scope of, we only care about the undirected, or it can implement this double equality, and we saw that in this case it's W1 hard. And in the remaining cases, FPT, and they can be FPT in two ways. One is a really trivial branching, and the other part is actually this generalized coupled min cut. Yeah. Okay. So let's see. Yeah. Let's see if I can convey some. So what we can do in a very simple case in the next 10 minutes. Yeah. So, okay. So here is the toy case of coupled min cut problem where, so our budget is K, and the mean cardinality cut size is known to be exactly 2K. So this means that we can only use pairs to cut S and T. Like we don't have any other select because, the solution, maybe I should remind you the problem. So the instance is given some graph G and ST, and edges are partitioned into pairs, and we want to find an ST cut Z consisting of n-most K pairs. And we also need to satisfy this strange property. And if Z is contained in n-most K pairs, then it can cut n-most 2K edges, but the flow size is always 2K. So it means that we really have to cut every flow Okay. Yeah, it means that Z should be exactly a union of pairs. We don't have any select to use something else. Okay, so this problem is FPT. How? So consider some random max ST flow P. So I will call this, so you can see this max flow as a collection of H disjoint paths, and I will call this flow path. And for every flow path in P, so they are all disjoint, we know that this cut that we are looking for intersects with P exactly once. Because, so the toy case assumes that the flow value is exactly 2K. And if Z is contained in the union of K pairs, then it can use 2K edges. And it has to cut all the paths in the flow. Otherwise, it's not an SD cut. So you have to, so the solution consists of 2K edges should intersect with each flow exactly once. Is it clear? Right. So let's start with finding a maximum, like arbitrary max ST flow. You can find such a thing, and let's consider it. And now, once you find such a flow, we interpret it as directed. So first, we consider it as collection of H disjoint paths, and then when you walk from S to T, like you consider it as like oriented from S toward T. So they might look like this. There might be some like edges or connected components which are connecting distinct part of this flow path. So first we can tidy up this flow path in the following sense. So if there is a path, so this might be contained in some connected components. If there is a path between two vertices on the flow path, then can you cut somewhere here? We cannot. Because if you cut here, then every vertex before that edge should be reachable from S. Everything afterwards should be reachable from T. But then if you have this additional thing, then they connect between S and T while the solution has to intersect every path. So it means it means that this Z cannot intersect this part. Right? So whenever you have such a connection, we know that these two vertices should be in the same connected component in G minus C, so you can just identify them. So with this, so you can do this identification. And if there is, so I have oriented the edges on the flow path. If there is a directed cycle, like using this directed arcs, so for example here, it means that none of these edges can be cut by Z. If something is cut by Z, then everything before it should be reachable from S and T, then there is a contradiction. So you can again identify everything. So you can identify in this way. So after doing that, there might be some connected components when you remove like all vertices on the flow, but their attachment vertex, like their neighbor, should be a single vertex. You cannot have two neighbors. So and if this is a connected component, and we already know that all the edges on Z should lie on the flow path, so it cannot never intersect this part. So this part will be either entirely contained in the S reachability set for S or T. So you can just identify to the vertex. So you can just ignore that part. So this means that you can remove this part. So this means that now you can reduce the graph so that every edge belongs to an edge of the flow path. Each flow path is induced path. There is no directed cycle. What what other things? Yeah, that's it. Right. Now because we can use k pairs and we have to cut 2 k edges, it means that the pairs, so like you can make a pairing of the flow paths, of these 2k flow paths, meaning that if we guess that these two flow paths are coupled, then we are going to cut them using paired edges. One is lying on here and the other is lying on here. So we can make all this guessing. So let's put it this way. ST. So we have to cut this, say 2k edge disjoint paths using 6 edges, where all the 6 edges are partitioned into pairs. So maybe you use the cut like this, and these two things are paired, these two things are paired, and these two things are paired. So we don't know how this pairing will appear, but we can just guess how the pair will appear on the flow path. So so there will be like n, I think it's n factorial factorial, no, k factorial factorial, different ways of cutting the flow path using using paired edges. So we first guess it. Suppose that this guessing is correct. Yeah. So after guessing this, we can eliminate some obvious non-choices, non-options. For example, if there is a paired edges, which are like this is not consistent with the current guessing that we made for the path pairing. So we can, if there is such a pair, then we can make both edges to have infinite cost or just identify the edges, like contract the edges. So this means that once you have this coupling of the paths, there will be you end up with paired edges which are lying exactly on the coupled path. So there can be pairing like this, there can be pairing like this, but you never have a pairing like this. So now so we have guessed that these two blue paths are coupled. So you can choose. So you have to choose the coupled paths which are lying on these two paths. But if one pair is dominated by the other, in the sense that so this E comma F, so E comes before E prime and F comes before F prime. So in the case we say that this pair is dominated by the first pair, then you can never choose these paths as a solution. If you choose it, then everything that comes before is reachable from S, and this really contradicts this weird condition that for every edge, at most one pair is reachable from S. So you can get rid of these pair, and maybe we just contract the vertices, contract the edges, and so on. Right. So this means that if you look at any coupled paths, then this pairing of the edge pairs form anti-chains. So none of them dominate the other, so it really looks like this. Right. Then you can easily check that this next condition. So whenever you have a solution which really chooses the pair, then for any paired edge, this vertex and this vertex cannot, so if one vertex is reachable from S, then the other vertex, B prime, should be reachable from T. So I will, so let's see U, V, U prime, B prime. So in this particular choice of the cuts, U is in T, sorry, V, so these two, V is in T and U prime is in S, reachable from S, also the opposite holes. And if you look at these red pairs, it's the same. So whatever, yeah. And actually, if this constraint is satisfied, then also you can like manually check that. Then you have to always choose the pair to cut these two flow. Okay, maybe I can.
If I choose two green edges,
Yeah, any choice is fine. But you cannot if you choose green and yellow here, then for some pair this condition is violated. So if this condition is satisfied, then actually you are forced to choose this pair.
That's the point.
Yeah, that's the point.
So choosing the pair is, we don't know like algorithmically how to enforce like choosing a pair, but in this particular way, by imposing this anti-chain property, you can enforce it by making you satisfy this particular condition. This makes you automatically satisfied. So these are if and only. Like if you choose a pair, then this is satisfied, and you're actually choosing a pair. So with this last condition, you can now represent this coupled min cut, this toy case, with a constraint satisfaction problem, and actually a very simple constraint satisfaction problem, where you have two CNF formula. So I guess everyone knows what two CNF formula is. So it's a conjunction of two clauses. So two clauses is like the clauses consist of two literals, and they are connected by OR connection. So two CNF formula is of this form, like A bar and B, and so on and so forth. And every clause has size exactly. They are using exactly two literals, so they are size of 2. So so you can formulate it as two CNF, so that there is solution for this toy coupled min cut if and only if these two CNF, there is an assignment for this two CNF which violates at most 2K clauses. So, okay, maybe that might be the last thing I can do. So how do we make this two CNF formula? So for S, we make constraint S equals 0, S equals 1, and then we make it crisp, so you have to always satisfy it. T equals 0, and for the paired edges, the edge pair, we impose that U and V prime, they are different. So if one is 0, then the other is 1, and vice versa. By the way, so when we make this, when we negatively like correlate these two variables, like there is some orientations, and the orientation should be consistent with this flow path. Right? So if UV is, U should be before V on the flow path, and U prime is before V prime in the flow path, then in the particular orientation, U and V prime are different. But we already have this flow path, so you can give this orientation for edges. So for every such paired edges, we make this constraint, and this cannot be violated. And so how do you impose that so this should be V prime, this should be V prime. So how do you impose that U and V prime are different, as in the previous thing? So you just add it and make it crisp. Is it clear that this imposes that U and V prime are different? Yeah. Okay. So this imposes that we always choose these pairs. And now for every edge on the flow path, we make this constraint of post 1. So every other thing was crisp, you could never violate it. And this constraint means that if U and V is an edge on the flow path and U comes before V, then I make the constraint so that if V is 1, then U should be 1. So this really imposes that along the flow path, only at most one change in the value can happen. Because if V equals 1, then you can have 0. But if V is 0, then you can never have, if V is 1, this is, if V is 1, then this is 1, but you cannot have V equal 1 and U equals 0. So now starting from T, you start with a value 0, and then along the path you can have 0, 0, and at some point you're allowed to have 1. From 0 you can have 0 to 1, but now from 1 to 0 is not possible because of it. So okay, maybe I mixed up a little bit, but something along this line. So right. So basically so let me have like 2 last minutes. So this was a toy case where K was exactly 2 lambda. No, lambda was exactly 2K. And for a general case, you cannot expect such a nice condition. But what we did for the toy case is actually a guideline for designing for a general algorithm. So in the general algorithm, we partition the edges into O of K edge sets, and each of the edge set is endowed with some linear order. And this linear order allows us to prune some edges which are dominated, and you have anti-chain property on these 2 edge set. And then you reduce to almost 2 sec. So I will skip like how we do it precisely. So yeah. Sorry. Right. Let me conclude with some obvious questions. So can we have directed version of the flow augmentation? So if you have directed version of flow augmentation, then actually you can settle some long open problems where like bi-objective directed, because this is considered like one of the sought after problem, parameterized complexity. And L chain sets. So here it's also constraint satisfaction problem where each constraint looks like this. So A implies B, B implies C, C implies D, and the length is at most L. So each constraint looks like this, and so this is constraint 1, constraint 2, so on as first, and we want to have a Boolean assignment on the variable so that at most K constraints are unsatisfied. So here the tricky part is that it can be like all the first, like the two clauses in this constraint might be satisfied. Something in the last part might be satisfied, but something in the middle might be broken. So how can you handle such a thing? This is tricky, and also our algorithm cannot handle this problem because it really involves directed cut. And we believe that like the directed version of flow augmentation will like almost immediately, but it's very likely to settle this thing. So yeah, and that's it. Thank you.
Any questions?
So what's the original version of the flow augmentation? Do you know?
Good question.
Yeah, this is it. So here we drop the condition that ST cut should be minimal ST cut. So some edges of Z, so this might be, so Z might look like this. Like this is the reachability set for T, the reachability set for S, and there are edges between components S and T. So if there is nothing else, then this is a minimal ST cut. But D might also contain some edges that crosses different parts. So for example, it may further contain something like this. But we have a little restriction on this, so it should be illegible. Illegible meaning that no two and so for any edge in Z, the endpoints should always cross different connected components. So you cannot have an edge like this in Z of Z.
Subset of G, which is indeed corresponding to the minimal ST cut.
It's not, it contains minimal SD cut, but it can also cut out some more connected components. Yeah. So like, just like in this example. So if Z is a minimal SD cut, then you cannot have such connected component.
But if you drop the condition that it should be minimal, then you might have like more components when you remove the edges in Z. So we allow such a case. So even when we allow such a case, still you can do the flow augmentation, as long as there is no edge of Z which are entirely contained in a single connected component in G minus Z. So that's what we mean by eligibility. So in this particular case, you can, with a good probability, you can find some edge set, so that when you add it, Z is still Z still cuts out, separates exactly the same connected components, and the part of Z which is exactly crossing the reachability set of S and reachability set of D, this part will be a minimum ST cut. Does it make sense?
When you say trichotomy theorem, in two of the consequences you have this either W1 hard or FPT.
Yeah.
But one consequence you didn't say what it is. It's open.
Yeah, so that's out of our scope. So this part is left open.
But you think it's gonna be harder than W1 hard, or is it something?
It's difficult to see. We haven't really worked on like trying to obtain like more dichotomy or trying to guess the characterization for these things.
Basically, the input graph G should be a multi-graph, right?
Yeah, it's multi-graph.
Okay. Maybe we can continue asking questions while dinner. So let's thank the speaker.